It's my great pleasure to be here to present. So my name is Claudel. I'm in civil engineering, not in energy at all, in transportation, in fact. And this is a joint work with my student Tianyi, but we have also a couple faculty in the US that are interested in this precise topic. So I'm going to talk about microwave energy beaming for aviation. So I would like to first start with transportation as a whole. So transportation is 1/4 of the primary energy consumption in the world, and there are some sectors that are relatively easy to decarbonize, for example, electric vehicles or electric buses or trains. However, aviation and long-range boats are very difficult to decarbonize. So for aviation, the biggest issue is that if you look at airplanes, they need quite a bit of power. For example, an Airbus A320 takes about 8 megawatts of power in cruise. So that's a lot of energy. That means you need to have either very big batteries, but if you take very big batteries, of course, it's a vicious circle for airplanes, so you cannot really do that, except if you have a very short range. The other possibility is to use alternate fuels. So to decarbonize, you could not use just jet fuel, but use instead, for example, so-called sustainable aviation fuels or electrofuels. The biggest problem is that they either don't scale very well or they are extremely expensive to make, which is why the industry is always saying that they are going to transition to it, but they're always pushing that more and more into the future as time goes on. So if we want to decarbonize aviation, first we have to remember that aviation is quite a bit of energy and power for the US. So for example, the electricity grid in the US is about 500 gigawatts in average. Aviation, if we look at the total energy used per day, it's 200,000 tons of jet fuel, north of 200,000 tons of jet fuel, which makes about 130 gigawatts of power in average. So if you want to sustain the air transportation system, you have to pay a lot of energy for price, no matter what you want to do. And the biggest issue is that you have to be scalable, you have to be energy efficient somehow, and you have to be economically scalable as well. So I'm going to talk about these things more in detail. So these are, for example, the cost projections of SAF, Sustainable Aviation Fuels on the left, with respect to baseline jet fuel. And these are the processes for electrofuels, which are a possible alternative for aircraft. So first, I'm going to talk about energy beaming as a potential solution for aircraft. So what is energy beaming? Energy beaming is the process of sending energy from a place where you can easily generate energy to a place where you cannot generate energy easily. So for example, for the army, that's applications to power forward bases or powering UAVs or balloons or aircraft or anything like that. And of course, you want it to be wireless. We cannot carry a wire to power the aircraft. So you have two main possibilities for energy beaming, which are either optical based or microwave based. Here you have a graph that shows what we have achieved so far. And in terms of experiments of energy beaming, what we would need is really this circle in this map. So we really need to be much more in terms of power and in terms of distance in comparison with what we have done. So you have two methods, as I said, optical, microwave. The problem of optical is that it's really impossible to use for aviation because simply it doesn't go through clouds or weather. And on top of that, if you want to send 8 megawatt or 10 megawatts of power optically, that means you need to have a gigantic laser and everybody would be blinded just by reflections. So that's too dangerous. Microwave can work though, but microwave has an issue. You need a very large aperture, so you need to have a very large surface area that emits the microwaves because the size where you can focus the microwaves is limited by diffraction. So it's limited by your aperture area. So if you look at previous work, people have been trying to do this since the 1960s. In fact, some engineers have worked on that. So in particular, this 1964 test of a drone powered wirelessly via microwaves. So that was an experiment for 10 hours where the drone reached 15 meters altitude and was able to stay over 10 hours above an antenna. So for as long as you can basically power the antenna. The efficiency is on the order of 40%, which is also the baseline that I'm targeting. So probably between 20 to 35%. But this depends a lot on the progress of the technology. We can possibly reach higher efficiencies, probably on the order of 50% as well. So how would that work? This is how the vision would be. So you would have basically a very large solar farm. When I say very large, it's kilometer scale. So you want to think about 200 megawatts farm approximately. That farm would emit a micro-wave beam as a phased array. So essentially, you would create a beam that is conical in shape, where the top of the cone is the airplane, of course, that receives the energy. And the advantage of doing that is that the beam would be essentially very safe up to a certain altitude, because the power is really concentrated when you're close to the aircraft, but you can pass through the beam at low altitudes without much risk. An important thing is I showed this picture as an illustration. So this is an example solar farm that would really work well with this approach. You want solar panels to be side by side, close to each other, because there is a theorem, and I will go back to this later, and that states that essentially you need to have a compact, you need to have a domain in which the panels are, but they cannot be scattered around, because that wouldn't work if you had that. And these panels would have surface emitters. So the key novelty would be to have surface emitters on top of the solar panels, so that you reduce cost, essentially. You have two usage for the single infrastructure. So people have been trying to work on this integration of solar panels with the surface antennas, not for powering aviation, but actually to save space on satellites. And this is an example of past work, not from me, of course, on this topic. So this work was about integrating a solar cell with an antenna on top. And the objective was to measure the efficiency loss associated with bundling the two systems together, the emission system and the solar cell. So in fact, you don't lose that much in terms of efficiency for the solar cell. You lose maybe 1% efficiency. So you go from, for example, 20% to 17%. So that's not that much of a deal. And the main problem is the loss of efficiency for the antenna. You lose about 30% efficiency, but this was in very specific conditions. We can probably improve to that number to lose less energy. So the second thing is how do we integrate all that into a system? So as I said, we need really a kilometer scale farm. So on the order from 0.5 to 2 kilometers. It's the sweet spot because that provides enough energy while being safe for humans. And also that solves the problem of the diffraction limited spot size for the aircraft. So what we need for the solar farms would be a capacity from 80 to 500 megawatts, flat mounted solar panels and connected to each other, of course. Everything has to be essentially as a circle or as a square, because you have a theorem that states that if you start to distribute your panels around, you will lose all the power into the side lobes. So you will not be able to power efficiently the aircraft. The power sent is from 30 to 200 megawatts and received from 7 to 50 megawatts at 25% efficiency. But again, we can improve these efficiency numbers. It's also in the radiative near field. That means that we can shape the beam in the way we want, essentially. And that means that it's similar to having a gigantic antenna or to having a laser, for example, where you can make the beam converge if you want, because you are in that near field. And it would work 24/7 with the grid. So that's also an important modification that we would need. Instead of the farm to only send power out, we would also like it to receive power from the grid to also power the aircrafts that are flying by when you have bad weather, for example, or when it's the night. On the airplane side, a few people have been working on integrating jet engines with their electric motors. So, for example, this is some work from NASA. Basically, it's not extremely complicated. It just involves powering the fan, so the thing that is connected to the low pressure compressor or low pressure turbine. You power it with an electric motor, and you have a parallel hybrid configuration in which you can have an engine that varies continuously the power sent from fuel and from electricity. The biggest problem for this is, of course, for these prototypes, and this is an actual company that builds these things, the problem is that if you want to power electrically, you have to bring batteries currently. So we want to avoid that, obviously. We want to power everything remotely, because the batteries are heavy and they affect the efficiency of the system. So if you look at the power consumption in cruise, you need approximately 8 megawatts for an Airbus A320 or Boeing 737 class, so single-aisle aircraft. For a long-range aircraft like a Boeing 787, you need more, something close to 30 megawatts. So that's the order of magnitude of what you need to send. Now, in terms of practicality, what we would use for this system is we would, so first, we would have to protect slightly the aircraft, because around the aircraft, the power density is around 500 kilowatts per square meter. So that's the power inside the microwave oven. Of course, that's extremely dangerous. But you can actually protect everything with films nowadays. You have, for example, microwave ovens that have doors that have just films on them, and that reflect 100% of the waves coming. You would have some heat dissipation too, because when you receive electricity and you have to convert it into DC, you actually lose power in the rectangles. But again, the heat flux is not that high, that's manageable. And you have also some added weights. If you want to equip the aircraft with the required motors, you would need to spend about 1 ton of extra weight, which is not that much. Again, it's approximately 3% of the empty weight of an aircraft. So how would that work in practice? You would receive power from the aircraft. So the aircraft would receive power while in range of this system, so probably on the range of 40 kilometers in total, or 30 kilometers. And with excess power, it would climb, and then you would glide down using that potential energy, so that you don't need batteries of any sort. Essentially, you would, with this system, be able to gain 100 kilometers of range each time you interact with that system. And that's quite a bit of energy, of course. That's 100 kilometers. If you look at a flight that makes, for example, 2,000 kilometers, that's 5% of the flight already covered. We have done some simulations with some of my colleagues to see how the beam would look like. So of course, on the left figure, so this ray here, it's not the ray of death, it's just an artifact. So in fact, the energy is uniformly concentrated into that beam, but it's just becoming higher and higher as you get close to the aircraft. But here, for example, if you were in that situation around the beam, and if you were, for example, flying at an altitude of 2,000 meters, say if you're a parachutist or if you're a hang glider, you would be completely fine. You would receive only 28 watts per square meter, which is basically only as much as two cell phones, essentially, in terms of power. So you would be completely fine. However, of course, the power received near the top would be gigantic, so that's where it would be dangerous to wildlife or people. But obviously, aircraft fly in specific zones, and above a certain altitude, you have quite a bit of control, etc., that are in place. So that could be managed. Now, if we look in terms of economics, that's really where what I would like to discuss more. So if we want to look at how much that system would cost, you have to look at both the capital cost and the operating costs. And you have to compare it with alternatives. So what are the alternatives? Either jet fuel, the current system, which costs about 15 cents per kilowatt hour. So that's the price of using jet fuel given the propulsive efficiency of aircraft and the cost of jet fuel per kilogram. So you have possibilities of using either sustainable aviation fuel, which are much more expensive. So they give a range in terms of price because that depends on the pathway of creating this sustainable aviation fuel. If you take, for example, used cooking oil, that's pretty cheap to make, but that doesn't scale because we are not spending our time eating fried foods, so we don't have that much of feedstock to use. But if you want to really be scalable, you need to go on the more expensive prices. And for example, for e-fuels, that range from 40 cents per kilowatt hour to 75 cents per kilowatt hour. And one of the biggest issues for e-fuels is essentially the efficiency. So it's scalable. You can build as many factories as you want to extract CO2 from the air and create green hydrogen. But when you look at the end-to-end efficiency, it's pretty poor because you're losing a lot of energy in all steps, making hydrogen, getting CO2, making the chemical reactions, etc., transportation, and then burning into the engine. You have extremely poor efficiency. While power beaming would have the advantage of just having a reasonably high efficiency, for example, 35%, but that could be also improved. And so, for example, if we have 35% efficiency, that means that the cost is 3 times the cost of electricity price. So I put 15 cents as a baseline, so assuming 3 cents to 5 cents per kilowatt hour, but of course that depends on the way you generate electricity and what are the LCOE, etc. That's now in terms of capital expenditure. If you want to build that system, you have to make sure to minimize the capital expenditure cost, to make sure that your system has a very high usage. And what is interesting, if you look at aviation, is that airplanes move into corridors. So essentially, if you are around regular paths or of aircraft, so if you are around these paths, for example, you can have a very high usage rate. And if you have a very high usage rate, that will reduce, of course, your expenditure. So in terms of estimating the cost, now that's a little bit complicated. So what I used was an estimation that I got from a report of NASA that was about space-based solar power. So that's a 2024 report that gave a price approximately of $1 per watt for the emission parts. So I'm assuming the same $1 per watt for the emission parts. So that means that if you have, for example, a 300 megawatt capacity solar farm, it would cost $200 million at $1 per watt for the electricity. Plus, here, if we want to beam 85 megawatts of input power, we will need to have $85 million on top of that to build the antennas. And what I hope is that this cost can be reduced if it's integrated into the fabrication of the panels, because a lot of things can be integrated. For example, the antennas can be printed on the surface, etc. So that cost of $1 per watt could actually go down significantly. But if we look at all this, so I'm going to do just some more analysis in the future. But what is very important is that the capex cost per kilowatt hour is 6 cents per kilowatt hour. So the amortization, again, if we take a 30-year amortization period, we're going to pay 6 cents per kilowatt hour just for the usage of the infrastructure, plus 3 times the current price of electricity. And here you have a set of farms, solar farms in Texas. That's exactly, I mean, the big farms that are here that are 300 megawatt capacity, that's exactly the size that we would need. That's approximately these 200 megawatts scale farms. So if we look at the effect of that in terms of CO2 reduction, so that's where also it's interesting, because really, we have only 2 possibilities right now for aviation. Either we go with SAF, Sustainable Aviation Fuel, which is supposedly reducing CO2 emissions by 80%, or we go with electrofuels, but electrofuels are not that efficient in terms of reduction of CO2 emissions. So if we look at this particular farm, for example, 20% utilization rate, you would transfer in 30 years 1,500 gigawatt hours of energy, which is 200,000 tons of fuels, which seems a lot, but that's actually only the lifetime consumption for example, if you take a Boeing 737 or an Airbus A320, over their lifetime, they're going to use 150,000 tons of fuel. So it's basically 2 aircraft for their lifetimes, approximately here, that you will have transferred. And the CO2 emissions, so if you use jet fuel to do the same work, you will spend 1 million tons of CO2. But if you use that system, you will spend 200,000 tons of CO2. Assuming, of course, 48 kilograms of CO2 per megawatt hour. That's, I guess, the approximate baseline for solar energy. That depends, of course, on the energy mix that you're using. Of course, if you're using an energy mix that is more dirty, you're going to spend more CO2. But if you use solar as the main energy for that system, you have approximately the same reduction targets as with Sustainable Aviation Fuel. You have approximately 80% reduction in CO2 emissions. If you use electrofuels, because electrofuels have 3 times worse end-to-end efficiency, you will spend 3 times more CO2 approximately, which are 600,000 tons, and therefore you won't have that much of a gain in terms of CO2. The other advantage of that system is that if you look at the impact of emissions on, the impact of aviation on global warming, it's not just CO2 emissions. Quite a bit is also caused by contrails. And if you actually use in-cruise electricity to power, of course, you won't have combustion, so you won't have contrails. So that also reduces that effect as well. All right, so that's what I wanted to discuss for today. So essentially, what I wanted to discuss is the fact that first, we don't have good solutions for aviation so far. And really, the industry is, I would say, pretending to solve the problem by always saying that they're going to use Sustainable Aviation Fuel and electrofuels, etc., and that everything is going to be fine despite the 5 times cost increase. in an industry where they don't even give you free cookies anymore because to save a few pennies per flight. So definitely that's not what's going to happen. So there is also supposedly a transition to the adoption of sustainable aviation fuel in the future. But if you look at the curves and the forecast, the S-curve of adoption is always pushed back five more years into the future every year. So it doesn't look very good. So what I would like to do with this presentation is to make the case that we have some alternative ways with, to solve the problem that could also foster solar power development, because again of the scale of the problem. So we have 500 gigawatts of electricity in America, but if we look at the power for just aviation, we need approximately 1/4 of that just to support the aircraft. So that could lead to much more solar farms as well. I would like also to mention that we have existing farms or existing things that have the right scale. So this is a farm in Texas of 250 megawatts. So that's about the scale that we would need. Of course, we would need all the panels to be put together, but I guess that can be solved. This is an example of a radio telescope in Australia that is kilometer scale in diameter as well. So it's really feasible to arrange those systems. I think the key problem is to develop all the technologies that will make that system cheap enough. So it's essentially the same problem as reducing the cost of solar cells back from the 70s, 80s, 90s, 2000s, etc., to the price we have right now, or similarly reducing the price of flat screens or any other type of technology. I would like also to mention that there are other possible synergies with that. So space-based solar power is trying to do the same thing, but from space, which is much more complicated, obviously. But solving this problem for aviation would make that particular technology easier to develop as well, the space-based solar power. And finally, one last point, developing this type of technology as well would be very interesting, because if you have an infrastructure of solar farms that are able to send power in the sky, you can also conceive possibly a constellation of very lightweight reflector satellites that could reflect power from one place to another on Earth with a range of 2,000 kilometers, an efficiency of about 40% as well, end-to-end. And that could be very useful, for example, to address the problem of the many days without good weather. Because you could really reflect power at a continental scale from different locations. That wouldn't solve, of course, the day-to-night cycles. That will be solved with batteries, but for the couple % of power, especially if you use curtail power as the input of that system, that could be one way to monetize curtail power and to solve the problem at the same time of long-term storage. Yeah. So that's what I wanted to talk to.
If you have any questions, just write them down. Maybe write it down on a card real quick. While you're doing that, I have a question. Who's ahead in this, the United States or China? Because I know China's all in on this also.
I'm not sure who is ahead of these things right now, to be honest. So I know that some countries have been trying to work on space-based solar power, but I'm not very convinced on the economics of space-based solar power, because the economics of sending things to space are really not that good, and especially if you want to send things in geostationary orbits. So a few people have, I know that China has given some plans of space-based solar power, but I don't think they will go through this.
So they're focused mostly on space to ground?
Space to ground, yeah. So this space to ground thing, I think the economics are really difficult to... if you look at the NASA report that was published 2 years ago, even the best baseline was about as much as we get from Earth with a solar plus batteries. So it's very complicated and doesn't solve that much for the problem. Yeah.
How would it work for long distance flights over the ocean?
Yeah, absolutely. So over the ocean, so of course the aircraft are not always flying in range of that system, but that's why we would have an hybrid configuration. Essentially, you would have still a regular jet engine with regular jet fuel, but similarly to an hybrid car, it's a parallel hybrid configuration where you would still use fuel for whenever you need and plus emergencies. And whenever you are in range of that system, you just use that system. But that would be a hybrid approach. For most of the continental flights, everything would be fine. But for the long-range flight, you would just power the chunk of the flight that is above land. And there are still quite a bit of flight that is happening above land. For example, if you take a flight, for example, say from Chicago to Paris, you have almost half of the flight that is above land, and the rest on the ocean.
Okay. This is kind of related to my China question that you may have answered, but why not use satellites for power refuel?
Satellites for research. So the biggest problem is that you need a gigantic surface area to beam the energy. So you need to absolutely have a kilometer scale structure somehow if you want to beam energy efficiently. And that becomes very difficult to make this kind of mega structure in space, rather.
This beaming reminds me of a magnifying glass over an ant. Will there be a concentration cost to the atmosphere or concentration areas over high population?
Yeah, so there is no risk because the system emits over the sky. So really, there is absolutely no risk for human beings, as long as you're far away, of course, from the dangerous area, close to the aircraft. But really, if you can fly through this thing with a small airplanes, I mean, obviously that would probably be prohibited anyway. But you have to make the system safe no matter what. But birds and etc. can fly safely. The real dangers are only when you are close to the aircraft. But that's a radar controlled zone. So
Okay, so yeah, this question is related. Is there any concern for how power beaming would affect birds and migratory insects like butterflies? I guess you're saying the birds are too low.
the birds are too low. Yeah, I mean it's a bit complicated because I think birds have been recorded to fly even at 9,000 meters, but that's probably very rare. And in that case, you could probably mitigate that problem. But usually they fly low. I mean, what we design in our system is we design a system in such a way that any flight above a certain altitude where you would require an oxygen mask or anything like that, or pressurization, that's basically the altitude at which the things could be dangerous. But below that, that would be safe.
Can the concept be modified to be similar in beam from nuclear, hydrogen, etc., instead of just solar?
Yes, it can take any type of power from the grid, and that's an important thing. We need the system to be bidirectional, essentially, to be efficient, because the airplanes fly at night. They fly, so you would need that system to work. To work. And then right now, I know that farms are supposed to be one direction. I mean, the electricity cannot flow back, but that would need to be a change.
How far away is this technology from being commercially ready?
That's right now, everything is purely conceptual, plus some experiments by people that have done, for example, these experiments from some colleagues. Their systems are already in the lab. I think the TRA is very low, though. It's probably the order of 2 or 3. But
Are the planes able to operate at day and night? So I think you answered that. So at night, you'd have to feed the power into the solar array.
into this, yeah, for example, from wind or anything like that. Yeah.
I think last question. Can you describe how your system is different from Nikola Tesla's wireless power transfer system?
Yeah. So the big difference with respect to Nikola Tesla's wireless power transfer, so both of them are power transfer things. Nikola Tesla would be using the reactive near field, and here we are using the radiative near field. So it's a different zone within the antenna. But essentially, the concept is about the same: to have sufficiently large. When you want to transmit power, you need to have some constraint between the product of the size of the apertures of the receiving and emitting aperture and the distance, and that's the same type of constraint.
Okay, the very last question. Could you create a dual use system, power for flight or power array to destroy drones?
Yeah, absolutely. Yeah, that would be possible. Technically, that would be doable. Yeah. If you were able to concentrate the power at specific locations, but in flight, that's why we target altitudes at 10,000 meters. But yes, it would be doable to change the settings to concentrate all the power, for example, at low altitude. Yeah.
Awesome. Thanks, Christian.
Sure.
So,